and this is the last video for Chapter 6, and we're going to start by focusing on rearrangement. So in the last video, we talked about types of arrow pushing, and the last type of arrow pushing we talked about was rearrangement, where we saw that if you have an unstable carbocation, you can have a 1,2 hydride shift, where a hydrogen from a neighboring carbon moves over to create a more stable carbocation. So just as kind of a refresher, let's look at a molecule. And let's identify primary carbons we'll identify secondary carbons and tertiary carbons, as well as the last kind, which is a quaternary carbon. Okay, so do you see any primary carbons in this molecule? And remember, primary carbons are bonded to only one other carbon. So we have primary carbons on the ends of the molecule. What about secondary carbons? Do we have any secondary carbons? And remember, secondary carbons are bonded to two other carbons. So the only secondary carbon I see is right here. So that one's bonded to two other carbons. Do we have any tertiary carbons? And tertiary carbons are bonded to three other carbons. No, but do we have any quaternary carbons? Yes, so quaternary carbons are bonded to four other carbons. And you can see that this carbon over here, so the second carbon in the chain, is bonded to three primary carbons and one secondary carbon. All right, so now that we've kind of refreshed our memory on the types of carbon atoms, let's now talk about carbocations. And with carbocations, you can only have primary, secondary, and tertiary carbocations. You cannot have quaternary carbocations because if a carbon is bonded to four other carbons, there's no room for a positive charge, right? It would have to lose one of those bonds to become positively charged. Okay, so let's redraw that molecule that we had earlier, and we're going to show a positive charge on the secondary carbon. So this would be called a secondary carbocation. Now, is there any way that we could create a more stable carbocation? So it might be tempting to move one of the hydrogens off to the right on the neighboring carbon. And if we do that, we end up forming the following. So the hydrogen is going to attach to that secondary carbon, which is going to get rid of the positive charge. However, that hydrogen left the primary carbon on the end, so that's going to leave a positive charge on the primary carbon. So that becomes a primary carbocation, and that is less stable than a secondary carbocation. So that actually would not work. That would not happen because we want to make sure that if we're shifting anything, it's going to create something more stable. So instead of let's see, so this would have been a 1,2 hydride shift if it had occurred, but it wouldn't because we're creating something less stable. Instead, let's move one of the methyl groups. So that is also a possibility. So we call this a 1,2 alkyl shift. So we're moving an alkyl group, which is really just a methyl or an ethyl or propyl or whatever, but typically it's a methyl group. So we can move one of these methyl groups over. Let's say it's this one up here. And when we do that, we end up with a methyl group on that secondary carbon. So it actually becomes a tertiary carbon. And then we lose a methyl group on that quaternary carbon. So it becomes a tertiary carbon. And because we lost a methyl group there, we get a positive charge. So now this quaternary carbon again became a tertiary carbon with a positive charge. So now this is a tertiary carbocation, which is more stable than a secondary carbocation. And we'll talk about why in a second. And I'll highlight the methyl group on the product that moved. There we go. Okay, so the alkyl group that shifts, it can be any alkyl group as long as you're creating a more stable carbocation. And again, an alkyl group is something like a methyl group, an ethyl group, a propyl group, isopropyl, whatever you can move to make something more stable. And this does happen naturally in compounds because if they can become more stable, they will become more stable. Now, you can only move groups that are on a neighboring carbon to the positive charge. So that's just something to keep in mind. And I'll write that up here. Oh, neighboring. I spelled that wrong. Neighboring. Neighboring. There we go. Neighboring carbon. All right, so now that we know a little bit more about rearrangement, let's talk about carbocation stability because, you might be wondering why is a tertiary carbocation more stable? So again, in general, a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, and that will be more stable than a methyl group cation. So, why are tertiary carbocations so stable? So the answer is hyperconjugation. Now, you might remember that previously we talked about resonance stabilized cations. So for instance, the allele cation. Now, even though those are primary cations, resonance stabilized cations are more stable than tertiary carbocations, for instance. So resonance, oops, sorry, my screen decided to zoom in. So resonance stabilized is more stable than hyperconjugation. But it's kind of a similar idea because remember, with our resonance stabilization, we had a carbon with an empty p orbital, for instance, and then we had a carbon with an electron in its p orbital next to another carbon with an electron in its p orbital. And we created a pi bond here, and then that could move over to the other side. And so it kind of stabilizes across 3 carbons total, right? Now with hyperconjugation, it's kind of a similar idea, but not quite as stable. So if we have a positive charge on a tertiary carbon, so let's just make up some R groups off to the side, and then let's say this positive carbon is bonded to a methyl group off to the left. If we draw a more detailed picture here, we know that the carbon in the methyl group is sp3 hybridized, and it's bonded to 3 hydrogens. And then we have our positive carbon next to that. And because it's positive, that means it has an empty p orbital. So what is interesting is that these sp3 lobes are partially aligned with the p orbital. And this is going to actually stabilize that p orbital that's empty. So we create kind of a stabilizing force there between the empty p orbital and the sp3 lobe. Now again, this is not as stable as something that's resonance stabilized, like the allele cation, but this is still fairly stabilizing, especially for something that is a tertiary carbocation. All right. Now you can also imagine, let's say that these R groups are other methyl groups, for instance. Now those will also have their own stabilizing interactions with the positive charge or the empty p orbital. on the central carbon. So not only do we have hyperconjugation with the carbon to the left, but there's hyperconjugation with the carbons on the right as well. However, if those two carbon or methyl groups, let's say, were hydrogens, so let's say those are H's, there's no hyperconjugation occurring between the positive carbon and those hydrogens. So this would be a primary carbocation, and this would not be as stable as something that has multiple sp3 hybridized carbons nearby. And that's why tertiary carbocations are more stable than secondary carbocations or primary carbocations, etc. So it has to do with that sp3 lobe that's partially aligned with the empty p orbital. Okay, so let's talk about one more thing before we end chapter 6. And you might recall from our previous video that we talked about single-headed arrows versus double-headed arrows. So let's talk a little bit about single-headed arrow pushing. So one example of single-headed arrow pushing occurs with hydrogen peroxide. So this is something you might have at home to clean cuts and scrapes and all that. And it's arranged like this, where we have two oxygens in the middle and a hydrogen on either end. Now, hydrogen peroxide is an oxidizer, and what can happen is the shared electrons between the two oxygens can split apart. And remember, with a single-headed arrow, we're indicating that only one electron is moving. So what that tells us is one electron's moving to the left oxygen, one electron's moving to the right oxygen. And this is what's called a homolytic bond cleavage. So the bond essentially splits apart, and again, one electron goes to the left, one goes to the right. So what we end up with are these molecules with a single electron just by itself. And if you have a single unpaired electron in a molecule, that's actually called a radical. Now, let's just take a minute and think about this. Are there any formal charges on oxygen? So if you want to pause the video and calculate the formal charge, feel free, and then we'll go over it together. Okay, so remember, when we calculate formal charge, we take the number of valence electrons, which is 6 for oxygen, and then we subtract the number of lone pair electrons. So on oxygen, this is 1, 2, 3, 4, 5. And then we subtract half of the shared electrons, which would be 2, because it only has one bond. So 6 minus 5 is 1, and then 1 minus half of 2 would give us 0. So there is no formal charge on oxygen, so it's not an ion. It doesn't have a formal charge, and it's just a radical. It just has a single electron that's hanging out by itself. Now, radicals can be dangerous in the atmosphere. If you are somewhat aware of pollution and smog and the chemicals that contribute to that. Some of them are radicals, and they can cause these cascade reactions that produce more harmful molecules in the atmosphere. They can also cause reactions that deplete molecules that do help the atmosphere. So, there's kind of two different ways that they can harm the environment. All right, so we have homolytic bond cleavage, but you can also have heterolytic bond cleavage. And we've seen many examples of this. So this is where two electrons move to one atom. And so this is most often what happens, but occasionally you get homolytic bond cleavage like with hydrogen peroxide above. Okay, so I think that's everything we need to cover in chapter 6. I didn't cover everything in, super detail, but that's what the book is for. It's there to supplement some of your learning. Remember that I do recommend going through those skill builder exercises in each chapter. I've stopped reminding you about them because initially I just wanted you to kind of build up that habit. But now I'm kind of sending you off on your own. So remember to go through the skill builder exercises and also any practice problems at the end of the chapter. That will help a lot, especially going into chapter 7. So in chapter 7, we're going to start talking about substitution reactions. And this is often where students start to feel really overwhelmed if they aren't already. But we'll work through it together and we'll go through it over 2 weeks of time. So we'll have plenty of time to digest that material. Okay, so I will see you in the next chapter.